Good morning or good afternoon, depending on where you are. We want to continue our thermodynamics lectures. My name is Professor Orata, so we are continuing with our lectures. So let us look at mass flow rate in machine cycles. Now we have talked about machine cycle in our discussions. In dealing with the compressors and reciprocating expanders and so forth. We have discussed several. We have obtained work in machine cycles. Let us look at mass flow rate in machine cycles. So let's just remind ourselves first. Let's say we have that cylinder pressure. Then we have our cylinder volume. Remember, we're dealing with a piston cylinder model, like we have discussed in the other earlier lectures. So I encourage you to follow those particular lectures, but we're making efforts to make sure that we are clear on them. So let's look at an idealized machine cycle. We have A1, state point B1, C1, D1. And like we had said, when we're talking of the piston cylinder model, we had the inlet and outlet valves, and we said that we can inject fluid and a complementary fluid which will occupy the clearance volume. And we talked about the importance of clearance volume in such systems in those earlier lectures. Now, let us call the fluid that occupies the clearance volume as delta MC, and the overall fluid in the system as MF. And of course, when you will have a diabatic expansion, we'll have that fluid, that is the fluid in the clearance volume and the fluid in the system. They undergo compression and expansion process in the system. And then we have the MF. Of course, here it will be ejected, and we now be compressing the clearance volume, the liquid occupying the clearance volume. We have talked about when do we have the inlet valves open, when are they closed, when are we at the top dead center. We have talked about the outlet valve, talked about the bottom dead center, and when outlet valve is open, when it's closed, and so forth. So we have discussed that in work in machine cycles in one of those lectures, and I encourage you to look at it. Now, let us just go back and calculate the work done in this particular cycle. Remember, dW, we said, is P dV. That's for pressure volume work, because remember, if you multiply pressure and volume, remember pressure is force per unit area, and volume is area times length or displacement. And so the two areas you cancel, left with force times length, which gives you work in Newton meters or any other units which you prefer. Now, the total work done in this machine cycle is given by the cyclic integral for that work. And this cyclic integral, that particular work, consists of 4 line integrals covering the processes A1 to B1, B1 to C1, C1 to D1, and D1 to A1. So the cyclic integral here, dW, consists of the integral from A1 to B1, the line integral from A1 to B1, PdV, plus the line integral from B1 to C1 P dV plus the line integral from C1 to D1, line integral from C1 to D1 P dV plus the line integral from D1 to A1, D1 to A1 P dV. Now, we know that the pressure here is constant, call it P1, and the pressure here is constant, that is P2. So, for the work cyclic integral, so for this first process, A1 to B1, then you have P1. Okay? We have P1 into V of B1 minus V of A1. Remember, V is the specific volume, and then plus B1 to C1. One, we have assumed that this process here obeys the polytropic equation, which is PV. Always remember, it obeys the polytropic equation. PV n is equals to a constant. Of course, n is the polytropic constant, can be called an expansion or compression constant, doesn't matter what you call it, but it obeys the polytropic equation. So if it obeys the polytropic equation, then the work in that particular case for polytropic equation is P2V2 minus P1V1 over 1 minus n. That is an expression we derived in the lectures on polytropic processes. So please also try and look at that lecture. Now, so if we use the polytropic equation for the adiabatic expansion, B1 to C1, then we will have P2 C1 minus P1 B1 over 1 minus n. And for the other process, C1 to B1, we have P2 into V B1 minus V C1. And then finally, for the other polytropic process there, we will have, for the polytropic process here, we will have P1, these are volumes, sorry, that is volume V1, you have forgotten that. This was volume C1, and that's volume B1. Let's grab it properly. We just wrote it, we didn't take the volume B1. So we have P1, volume A1, minus P2, volume B1, over 1 minus n. Now, remember that this particular process A1 to B1 is just a mass transfer process, so there's no work done. The same with this process from C1 to D1. Just look at our discussions on machine cycle. Then you will get to know what we're talking about. So we're talking about this a mass transfer process, this mass transfer. So W is equals to 0. The same with this, mass transfer. Therefore, W is equals to 0. So those quantities there, that is 0, and that becomes 0. So we are left with W is equals to P2VC1 minus PVB1 over 1 minus n plus P1VA1 minus P2VB1 over 1 minus n. Now, we want to bring in now these masses into our expressions, and so we need that expression there. So let's leave it there because we will go back to it. We will reference it again. Now, at the specific volume at VA1 is given by the mass of that fluid which occupies the clearance volume times V1. You have pressure 1. And for the state point VB1, it is given by the mass of the fluid plus that of the clearance volume times the volume at pressure 1. And at state point C1, VC1, we will have again that mass for both clearance volume and fluid in the system times the volume pressure 2, that's V2, and for VD1 we will have delta for the mass, the clearance volume, as a fluid in the clearance volume, times that we are at D1, that is pressure at volume V2. Remember V is specific volume. Specific volume. Now, if we use these quantities of volumes in our expression here, then we see that W will be P2 and VA1 is delta MC V1 minus P, this is P1, so we had VC1, where are we? We had VC1 minus P1, so that is P1, I've forgotten to write it down. VB1 will be delta MF plus delta MC V1. Then we have plus P1 we have P1 VA1. This is VC1. So we have left the VC1. Where is the VC1? We have P2 VC1, or we've not put the correct one. We put for VA1. So that is VC1. So let's just write it down properly. Again. That is P2. You have P2 for VC1. I've read it as VA1. So that should be delta MF plus delta MC V2 minus P1. Let me read it properly. VB1 as at state point 1 will be delta MF plus delta MC V1. I think I've read it correctly now. Of course, divided by 1 over m. I will factor it out. Then we have plus P1 VA1. Now we go back to the correct one. That is delta MC V1 minus P2 VD1. That is delta MC V2. And of course, all these are factored out 1 over 1 minus n. Factored out 1 minus n. Now let us see if we can simplify. These quantities. So if you open up our bracket, then we have P2 delta MF plus P2 delta MF V2 plus P2 delta MC V2 minus P1 delta MF V1 plus P1 delta MF delta MC V1 plus P1 delta MC V1 delta MC V1 delta C plus delta MC V1. So we have minus P1. This is minus P1 delta MC. That is a minus, not a plus. And we have minus P2 delta MC V2. And all these are factored 1 over 1 minus n. So let's see if there are terms which are alike and can be added or subtracted or cancelled out. So we have P2 delta MV V2. We don't see one like that. We have P2 delta MC V2. Yes, that cancels out. That cancels out that one. And we have minus, we have here minus P1 delta MC V1 plus that. They seem to cancel out. So we seem to be left with, that is 1 minus n into P2 delta MF V2 minus P1 delta MF V1. So if we factor out this mass here, mass flow rate here, we have delta M 1 minus n into P2 V2 minus P1 V1 for W. Very important equation. Relates the mass flow rate in the system there. That's the equation which you have gotten there. Now, if we multiply that equation there by the number of cycles per unit time, let n be the number of cycles per unit time. Cycles per unit time. Let's call it n. So if we multiply this quantity, this is the work done. That is the rate of work done. W there. Remember this W is the rate of work done. So if we multiply by the number of cycles per unit time, then if we multiply by the number of cycles per unit time, so if we multiply this equation, W, by the number of, we multiply W times n, then we will now have the rate of work done per unit time. Per unit time. Multiply that with that. Multiply that W by that. So that what we really have there is W is equals to N delta MF 1 minus N PV V2 minus P1 V1. And so when you have delta MF as the mass flow rate, then N delta MF is the mass flow rate per unit time. Per unit time. So very important, now we have used the masses within the system to relate to the work which is done in that machine cycle. So this is very, very important for us to be able to remember. And always just remember that where we have mass transfer, we have assumed there's no work done for those processes where we have mass transfer. And then in the adiabatic expansion and adiabatic compression, we have assumed that the system obeys the polytropic equation of state, that is PV raised to power n, where n is our polytropic index, or expansion compression index is equals to a constant, and we have worked with that, and that gives us these particular quantities for work done in that machine cycle. So we'll stop at that point. We'll pick up later.